Our first lesson of the year is going to be over units and factor dimensional analysis. This will be a little bit of a review with a little bit of new stuff, but mostly just reviewing. We're going to cover three topics: SI units and prefixes, unit conversions using factor dimensional analysis, and applications of those unit conversions. So let's take a look first at SI units and prefixes. So the SI, or the International System of Units, it's SI in that order due to its Système International des Units, I think. In French is where it comes from, the reason why the abbreviation is sort of backwards. But the International System of Units is what we often call the metric system, but it is the system of units used in physics and, for all intents and purposes, in all modern sciences. Standard form of the SI used in most area of physics is called the MKS system. There are two different types. MKS is one of them. The other one is, we'll talk about in a second, is just the CGS system. But the MKS system is called this because of its base units, and those are meter, kilogram, and second. So it makes sense that our fundamental unit of length would be the meter. Now, normally you'd expect that the fundamental unit of mass would be the gram, but in the MKS system, the fundamental unit of mass is going to be the kilogram. So anytime we're doing any calculation and asks for a mass, you want to put that mass in kilograms. And then the last one is seconds, that's time. And so these are the base units that we will use as we go through this class. Now, just so you're aware of it, we won't use these in this particular class, but just be aware these are out here. There are some branches of physics, mostly in electromagnetism or electrodynamics is probably the most common one. Astronomy uses these as well, and I think there's one other, I think it's material science also uses this other system. Do use a system called the CGS system for centimeter gram second. As we'll talk about, it really doesn't matter which system you use as long as you're consistent. But for the purposes of this class, we're going to use the MKS system because that is the standard for mechanics, which is what this class is. This is a class on physics of mechanics. So carrying on here, SI units, a little bit of review here, are made up of two parts. They have a unit, and then sometimes they have a prefix as well, which then will scale the unit to make it an appropriate size. And so let's say we start off with a basic unit, the meter right here. If we were measuring something that was, say, the size of a state, meters would probably be too small of a unit to use. It would make sense we would need a larger unit, and so that is scaled up by adding a prefix, kilo, which we'll look at in a second. So the kilo in this case means 1,000, and so a kilometer basically would mean 1,000 meters. Pretty straightforward. You've probably seen this before. And so we have a prefix, we have a unit right here. Whenever we're abbreviating SI units, they work fairly similar. There'll be an abbreviation that's simply for the unit itself, so that's meter right there. If we wish to write out an abbreviation for kilometer over here, then we would add the prefix abbreviation, so it's km. Most of the time is that you will generally have things which are two character symbols if you have something with a prefix, one character if you don't, but there are exceptions to that. The unit of frequency is hertz. And so Hz is the base unit here. If you were talking about something in kilohertz, you'd add a K out front, so it's a 3-digit one right here. The same thing, or three character symbol as well. The same thing is also true for pascals, the unit of pressure, which is PA. If you want to talk about millipascals, it'd be like that. Or even Dalton, which is sometimes one that's used in chemistry, DA. And if you wanted to talk about large molecules, are usually measured in kilodaltons. And so KDA like that. If you do notice, most of the time that you'll see, like this guy right here, it's a lowercase m. SI units that are named for a person have a capital letter to start them. So Hertz is the guy's name, Pascal's the guy's name, Dalton's the guy's name, Newton is a guy's name. However, liter, there was no guy named Liter who discovered the liter, and so liter is lowercase, meter is lowercase, second is lowercase. So just sort of be aware with that as you go through things. So let's look at some prefixes here just very, very quickly. Because you're already familiar with these for the most part, or should be. SI prefixes, we have a series of two types. We have smaller prefixes and we have larger prefixes. The smaller prefixes, for the first three, Basically go down by power of 1. So deci is 10 to the negative first, centi 10 to the negative second, milli 10 to the negative third. Once you get past 10 to the negative third, you typically go up by powers of 10 to the third, or down by powers of 10 to the third. So 10 to the 6th, 10 to the 9th, 10 to the 12th, 10 to the 15th. For femto, probably the smallest one we'll use. On the larger prefixes, they sort of work similarly. The first 3 go up by powers of 10. So we have 10, 10 to the 2nd, 10 to the 3rd. And then after that, they go up by powers of 10 to the 3rd, 10 to the 6th, to the 9th, to the 12th, to the 15th. Do note one quick thing, the sort of the oddball out, or there's sort of 2 that you might argue are oddballs out here. Deca, the prefix for that is DA. It is a 2-character prefix. So it is possible to end up with something that actually is a unit that has 4 letters in it, like say decapascal. And so you'd be DAPA, like that, which, that happens sometimes. Just sort of be aware that that's out there. Other one that's odd here that always throws people off is the symbol for micro, which is the Greek letter mu. It's their letter for M, and so just sort of be aware that's in Greek. Sometimes, if you don't have a Greek keyboard available or it's not there, you will see this written as a U. So like you'd see like UM. That's not technically correct. But it is sort of a common notation of it, and so I would say that's bad to write it off that way, but you will see it sometimes. So once again, be aware that that's out there. So since that shouldn't take a whole lot of explanation, let's go on next thing here. So that covers prefixes. The next thing we want to talk about here is SI units. So SI units fall into one of 2 categories. They're base units and they're derived units. SI has 7 base units. These base units are defined. Some of these come around to when the metric system was developed back in the early part of the French Revolution, such as the meter and the kilogram and the second. Others of these are ones that have come along later as scientists have taken other units and used those. Well, actually, I guess the second wasn't really developed in the French Revolution, so get that out there. But the meter and the kilogram were. These 7 base units, every other unit is based on these 7, but these 7 are defined. So as I said, they're arbitrary. They have their values based only on agreement among scientists. Is it so? Could the meter be anything? Yeah, the meter could be anything. In this case, it was originally designed as being 1/10 of the distance. 1/10 of the distance between Paris and the North Pole along its meridian. Kilogram is so look at this. So we have the symbol, we have its quantity of length. That's what you measure with the meter here. Approximate size, it's a meter stick. You know what a meter is. Next one here is a kilogram. Kilogram is unit of mass, kg. It's the only one of the base units that has a prefix on it, naturally, because we use this MKS system. Its approximate mass is that of a liter of water. And so if you have a liter of water, that has a mass of a kilogram. That's how it was originally defined. Technically, today, the kilogram is defined in terms of a particular mass, a physical iridium platinum object that sits in an institute in Paris. And so every once in a while they get it out and compare it with other masses to make sure we know what the kilogram is. That's how it's defined. Technically, the meter is defined in terms of the speed of light. It's a certain it's a distance that light travels in a certain distance. That's how it's technically defined today. Second, this one is one that we're actually fairly familiar with. This is probably the oldest of the actually it is the oldest of the base units. It's second's unit of time. In physics, in the SI system, it's defined as being 1/86,400th of a day is the conventional definition of it here. It actually these days is defined in terms of, I believe, the number of oscillations in a particular cesium atom by looking at the way that oscillates whenever you excite it at a certain level. And so that's why you hear these atomic clocks that measure time extremely accurately. And so that's what our second is here. Our next one here, most of the rest of these 3 that we started off with are the 3 we'll primarily use as far as base units in this class. The rest of them show up, but won't be common here. But we go over them anyway here. So the next one is the ampere, which is a unit of current. It is named after a person, so it's capital A. It is roughly the current used by 260-watt incandescent light bulbs. So not the fluorescent type; those use a lot less current through them. But a 260-watt light bulbs roughly pull about an amp of current or an ampere of current through them. And so this is our SI unit of current. Temperature is measured in Kelvin. I've taken chemistry, you know that. And so it's roughly 2 Fahrenheit degrees. Actually, it's 1.8 Fahrenheit degrees is 1 Kelvin. Next one here, mole is the amount of substance or the amount of something. It's got a nice little 3-letter abbreviation. Just sort of have to deal with it. Roughly approximate size, atoms in 12 grams of graphite. And so 12 grams of graphite would have what's the term is Avogadro's number, is the number of atoms in a mole. So it's the number of things in a mole. So it's the number of atoms in 12 grams of graphite, which is all carbon. So that's how it's defined there. And the last one here is probably the least used of all these, which is the candela, CD. And it's a measurement of luminous intensity. So it's the intensity of light. And its approximate size, it's approximately the light put off by a simple common candle. These are our 7 SI base units. They're defined, they're set, you just have to accept that that's what they are. But everything else, every other unit in physics is based on these few 7. So our next class of units are called derived units. Derived units are used to express all other quantities. So all derived units can be expressed in terms of those 7 base units we talked about before. So the first one, the most common one we'll use in this class, the derived units, is the Newton. Newton, Sir Isaac Newton, symbol is N. It measures force. It's a unit of force. If we had to write it in terms of the other units, we would say it's this. It is 1 kilogram times meters per second squared. So it's a kilogram meter per second squared. That is equal to 1 Newton. And so we can always write it in terms of other units here. Joule, another common one, unit of energy. Kilogram meter squared per second squared. Watts, capital W, is a unit of power. Kilogram meter squared per second cubed. You probably can't see that, but that's second cubed right there. Hertz, we already mentioned before, is unit of frequency. It's just 1 over seconds, or inverse seconds. The liter. The liter technically is not a derived unit. It's actually a non-standard unit that is used, it's accepted in SI, but we'll use it as it is a derived unit, and it would be the unit of volume. It's defined as 0.001 or 10 to the negative third meters cubed. Gives you a liter. Or the Pascal, unit of pressure, is kilogram per meter second squared. And so technically that meter per second squared is on the bottom of that particular equation right there. So that's our Pascal right here. Now, here gets the important part. Since we can write units in terms of other units, we can use unit analysis, sometimes called factor dimensional analysis, to understand and convert between these quantities. This turns out to be fairly critical as you get into physics, because you're going to be dealing with a lot of different quantities that have completely different units. And you're going to be multiplying them together and dividing them by one another. And the question is, what happens whenever you say, I have a Newton times a meter? What does that mean? What is a Newton meter? What type of quantity is it? Newton's force, meter's distance. So if I have force and distance, what does that give me? Is that a time? Is it a power? Is it an energy? Is it a frequency? Well, if you know what these units break down into, that a Newton is a kilogram meter per second squared, and we said if we take that and we multiply that times meters, we get kilograms times meters squared per second squared, and that, kilogram meters squared per second squared, is a unit of energy. That's a joule right there. And so then we know that if we take a force and multiply it times a distance, we're going to get an energy out of that. Without knowing anything about the rest of the problem, simply by looking at the units, by doing this factor dimensional analysis, we can understand what's going on as part of the problem. And in order to go into that, what we're going to do is we're going to look mostly at unit conversions as a way of understanding this, and then later on as we get deeper into the course, we're going to be able to use this factor dimensional analysis to answer questions that might be difficult or impossible to solve otherwise. So a little quick definition on factor dimensional analysis. It's a method of analyzing the physical properties of something independent of its units. And so we use the units to understand it, but the actual physical properties are independent of the units themselves. We can use this to convert between units. We use it to check how reasonable calculated result is. Did we come out, if we're looking for an energy, did we come out in units of energy or did we come out in units of time? If we came out in units of time, we did something wrong. And we can use it to make predictions about results without measurement or calculation, like we talked about before with force and distance. We know that if we have a force being applied over distance, that's going to give us an energy right there. When you get down to it, sort of our fundamental part right here, fundamentally, factor dimensional analysis means that all physical properties are independent of their units. I could say, right now it's 32 degrees outside Fahrenheit. Or I could say it's 0 degrees Celsius, or I could say it's 273.15 Kelvin. All those are different units, but all those express the exact same thing of a particular temperature. All physical properties are independent of the units, and if that's the case, then we can express physical quantities in terms of different sets of units. So speed could be in miles per hour, or it could be in angstroms per year, as long as it's in terms of its definition, which in this case is going to be length divided by time. It doesn't matter what units we use, as long as it's basically a length per time. So this is where we start off with here. And let's take a look at a little bit of some more work on this. So let's look at some examples. So let's do little unit conversions. So first question, how many inches are in a meter? And so we start off here with 1 meter. And the way we're going to set this up is to do unit conversions. First thing you're going to need is you're going to need some conversion sheet here. And so you should have a colored sheet, which is, a data sheet, which is Common English Units of Measure, which gives you conversion factors. And these are the ones that we will use in this class. If you are converting basically between metric prefixes, involves things as prefixes, you simply need to know those as well. So you might want to write those down if you don't have them on that sheet. So we start off with meters. How many inches are in a meter? We want to go from meters to inches. We're asking about how many inches. And so if we look on our sheet, this is going to be a distance or a linear equivalence. And so if we have to go from meters to inches, we have our linear equivalence. We also have our English to metric that's over on the right side. Is that right now inches is an American customary. That's English system. Meters are SI. We don't have meters and inches on here, but we do have inches to centimeters. And we could go from meters to centimeters. And so that's going to be the path we'll take. We have 1 meter to start with. We'll go then to centimeters and then finally to inches to get our answer here. The way we're going to set these up is basically by writing out tables like this. If you put something on the top of the table, it's basically considered to be multiplying. If you put something on the bottom, it's considered to be dividing. And so in this case, to convert from meters, we first have to go to centimeters. And so to get to centimeters, which is what we want, we basically have to write something that is basically equivalent to 1. You can always multiply something by 1. And so if we put something on the top and on the bottom that are equal to one another, that's the same as multiplying by 1. In the same way that 2 over 2 is 1 or 10 over 10 is 1. And so as long as we put two things that are equal, then we're good here. So we want to cancel meters. And so now we have meters divided by meters if you sort of look at it, top to bottom. That would cancel meters. We'd be left with centimeters as long as the numbers that we put out here and here are basically going to be numbers that make this top to bottom statement true, that they're both equal to each other. And so the question is, how many centimeters are in a meter? If you look at general things here, we know that there are 100 centimeters in a meter. If you wish, you could say centi is 10 to the negative second and say that we've got 10 to the negative second meters in 1 centimeter. I'll go ahead and do that. You can do it either way. 10 to the negative second meters in 1 centimeter, or you could have said 100 centimeters in 1 meter. They both work here. Once we've got that part done, is that if you notice, as we said before, is that our meters are canceled. They're gone now. We just have units of centimeters. If we were to multiply and divide this whole thing out. Notice that we're not, as we go through this, going to solve it in the middle of it. We're not going to do this step by step. We're going to set the whole problem up, and then we're going to solve it at the very end. We want to cancel out centimeters. If you look on your sheet at your English to metric conversions, we do have a conversion between centimeters and inches, which it says that 1 inch is 2.54. That's 2.54 centimeters, like that. Looking at this, then we, of course, that cancels out centimeters. Centimeters is gone. The numbers out front, the coefficients are still there, but at this point we have it in inches, and so this should be our answer once we solve this out. And so if you take your calculators and you say, across the top, 1 times 1 times 1, because those are the three things on top, divided by what's on bottom, so divided by 10 to the negative second is our first one that's on bottom. Give me a second to get my calculator working here properly. So divided by 10 to the negative second, and then divided by 2.54. And we do that, we get 39.37. Now, we do want to use significant figures. If you're not up to date on those, you probably want to look quickly online, get yourself to date on this. But in this case right here is that the rule is, since it says a meter right here, is it doesn't give you, it's considered to be exact, so infinite significant figures. And so technically, we should write out our whole answer here. I'm not going to do that just for space reasons and because it wouldn't be possible. But 39, that's a 9.37 inches. It's pretty close to what we have here. And so this would be our final answer. So that's basically our conversion factors right there. So continuing, let's look at our next one here. If your car uses 2 gallons per hour of gas, what is the flow of fuel into the engine in milliliters per second? And so similarly, we're going to start this off with what we know, that we have 2 gallons per hour. So we have 2 gallons on top, but as we set up our table, it's per hour. Per hour means divided by hours, and so we're going to put hours on bottom, like that. And so to set this up, we first want to convert from gallons to what we want, which is milliliters. Then we're going to convert from hours to what we want, which is seconds. And so let's look at gallons first. And so we want to get rid of gallons. And the way we're going to get from gallons to milliliters is, if you look on your sheet for volume equivalences, you can see we can go from gallons to quarts. Then at your English to metric, quarts to liters. And then we can go from liters to milliliters using our prefixes. And so that's what we're going to do here. So we go first from from gallons to quarts. Quarts, that should be a Q for quarts. And so we know there are 4 quarts in 1 gallon. Continuing out our guy right here, we want to get rid of quarts now. We want to go to liters. And so if you look at your sheet, you'll see that there are 1.06 quarts in 1 liter. So in 1 liter, there are 1.06 quarts right there in 1 liter. And then once we've got to liters, we want to get rid of liters and go to milliliters. So there's 1 milliliter. In 1 milliliter, there's 10 to the negative third. Wow, that didn't write out very well. 10 to the negative third liters, because milli means 10 to the negative third. And so at this point right here, we've got this into milliliters. If you look at what's canceled so far, you'll see that we have canceled gallons, we've canceled quarts, we've canceled liters. Right now, if we were to solve this, we'd have milliliters per hour, but we want milliliters per second. So continuing on this, usually what I will do just to keep my notation straight is put a double line whenever I am switching from converting one unit to converting another one. So here we want to get rid of hours. Since hours starts out on the bottom, to cancel it, we have to put hours on top up here. And so once we've got hours right there, is we now want to figure out how to get from hours to seconds. Well, fortunately, that's a pretty easy one. We can go from hours to minutes, minutes to seconds, or since there are 60 minutes in an hour, 60 seconds in a minute, it's basically 60 squared. And so 60 squared is 3,600. So we have 3,600 seconds in 1 hour, like that. And once we've got that, we can solve this out. And so doing so, just looking at our units just really quickly here, is we had hours on bottom, that cancels hours on top. The only existing units that remain are milliliters and seconds, so it's milliliters per second. So let's see how much gas we're using here. Coming to the engine. And so in this case, starting on the top, we have 2 times 4 times 1 times 1 times 1, multiplying everything on top. Now we want to divide what's on bottom. So divided by 1, divided by, 1.06. That's actually what that says, even if it doesn't look like it. And then we're going to take that, and we're going to divide it by 10 to the negative third. And then we're going to take that, and we're going to divide it by 3,600. And in doing so, I get 2.096 milliliters per second. Significant figure-wise, we were given a value of 2, and so that has one significant figure. Since we're only doing multiplication and division here, then we look at the number of the fewest significant figures we use to start the problem, which is 1 in this case. So we should only have 1 sig fig, and so if you're on 2.096 to 1 significant figure, you get just 2. So 2 milliliters per second. So that gives you an idea, and that's our final answer there. Okay, so that's an example, some simple examples of using factor dimensional analysis. If you were basically, if you remember if you took chemistry with me previously, then you know that that should be fairly straightforward to you. We're going to move on very quickly to sort of go through. We're not going to spend a lot of time on the simple ones like that, but just did it so sort of refresh a little bit of a review there. We are going to look more at some conversions on things, applications of these. So let's suppose we have this. Flooding in Iowa happens fairly often, and so suppose you have a basement. Water flows into a 20-foot by 30-foot basement at a rate of 5.1 liters per minute for 8 hours. How deep in inches is the water in the basement? And so in this case right here is that we're going to have to do some unit conversions because we have liters per minute. We have for 8 hours. We have depth here, but we have it in liters versus depth, which is a distance. And so the question is, how do we set that up? So looking at this, basically what we're going to do is we first need to figure out what volume of water is in this basement. Well, here's what we know. We know to start things off is that we have 5.1 liters per minute. And for 8 hours. And so if we have 5.1 liters per minute, we want to convert this so we can get it into hours here. And so we're actually going to go ahead and set up our little table here. Liters per minute, we want to cancel minutes. So we're going to put minutes on top. And we're going to go to hours. That way we can multiply this out. This one's fairly straightforward. And of course, there's 60 minutes in 1 hour. And so in multiplying this out, we get 5.1 times 60, at which point we get there 306 liters per hour. And then if we want to multiply that by 8, that'll tell us the total volume of water here. So 2,448. So we have 2,448 liters of water is what we have here. So we've got that is the total amount of water that's flowed into our basement here. Now notice we're not going to round this yet because we never want to round until we get to our final answer. So 2,448 liters. Now we know this amount is going to be equal to the volume of our basement, which is 20 feet by 30 feet by the depth in inches. Now, the problem is we have feet, and inches, and those are equal to something in liters. And so we want to get all of these into the same set of units. So the first step here would probably be to convert our 20 feet and our 30 feet into inches. And so because we want our answer to be in inches, and so that's going to be our easiest bet here. So 20 feet right here would be 20 times 12. And so if you take 20 times 12, you get 240 inches. So that's 240 inches. Sometimes you don't have to set up your full table if it's fairly obvious. 30 feet would be 360 inches. And so here's what we know. We know that 240 inches times 360 inches times our unknown depth in inches, x, is going to be equal to 2,448 liters. But liters and inches don't match up. What we want to do is we want to take this liters and convert it into cubic inches. And so we're going to set this up again to 448 liters. And so we're going to set up our table like this. We want to get rid of liters, but we want to get to cubic inches. So a quick look at our table here says what we could do is we could go from liters to milliliters. And then from milliliters, we could go to centimeters cubed under the other equivalences. From centimeters cubed, we can then convert to inches cubed, which is what we want. And so we're first going to go to milliliters. So how many liters are in 1 milliliter? 1 milliliter is 10 to the negative third liters, or we could say 1,000 milliliters in 1 liter. Either one works. So that gets us to milliliters. We know that 1 milliliter is equal to 1 centimeter cubed. Like that. And now we want to cancel centimeters cubed, and we want to go to inches cubed. Now, normally, if you look at your sheet, you will see that 1 inch is 2.54 centimeters. But because of the fact these are cubed, we'd have to say 1 cubed, which is just 1, is equal to 2.54. And I really didn't give much space there. I'm going to erase that out a little bit. So we'd say 2.54 cubed centimeters cubed. Doing so, we're going to cancel across, so liters is gone, milliliters is gone, centimeters cubed is likewise gone, and so now we can go ahead and multiply this out and see what we get. Doing so, we say 2,448 times 1 times 1 times 1 cubed divided by 10 to the negative third, and then divided by 2.54 cubed. And doing so, I get 149,386. And so what we're going to do is we are going to quickly sort of replace our 2448 liters with something that's in a unit that we can deal with, which is going to be this. 149,386.1255. And so to solve for x, we get, that's a comma there, not a decimal. So we have 240 times 360, 240 inches times 360 inches times x inches equals 149,386.1255 inches cubed. And so if we divide that 149,000 number by 240 inches and by 360 inches, then it's going to do a couple things. One, it's going to cancel this inches with that little guy right there, leaving just squared. This one's going to, the inches is going to cancel that squared entirely, leaving just inches left over, which is the unit that we want for this one. So this is a little bit of factor dimensional analysis. You can see we're coming out with the correct answer here because the unit comes out in inches, which is what we want. So we do that. We take that number, the 149,000, divided by 240, and then take that and divide it by 360, and we get 1.729 inches deep. Significant figure-wise, 20 foot by 30 foot, each of these have one significant figure, and so we're pretty certain our answer is going to have one significant figure here, and so our final answer here would be it's going to be roughly 2 inches deep right there. That's how deep the water would be in the basement. So that's an example of sort of a quick little conversion problem here, so or an application one. So let's look at one other application one here. Suppose that we have a hemispherical cattle trough. It's 4 feet across. How many gallons of water does it hold? This seems like a fairly reasonable problem here. First thing is it's hemispherical, and so if it's hemispherical, that's going to mean, whoops, just a second. So if it's hemispherical, that's going to mean that it's sort of a half circle or half sphere like that, and so that's sort of what we've got going on here. And we know it's 4 feet across. And so we know it's 4 feet going across here, feet, if that's legible at all. So it's 4 feet across there. To find gallons, how do we find the volume of a hemisphere? Well, we know this. The volume of a sphere is equal to 4/3 pi r cubed. If you didn't know it, you could have looked it up, right? And so we've got this right here. That's our sphere, and this is a hemisphere. Hemi means half. And so hemisphere would be half of this. And so as a result, it would be 2/3 pi r cubed, or just to find that here. So let's figure out what we have here. It says that it's 4 feet across, which means the radius is 2 feet. And so we would say 4/3 times pi, 3.14159, times 2 cubed. Gives us the volume of the whole sphere, but it's a hemisphere, so we divide that by 2, and that gives us 16.755. So our volume of our hemisphere is going to be 16.755 feet cubed. But we want this in gallons. And so we're going to start off with this number right here, 16.755 feet cubed, and we're going to put this into our table. We want to first get rid of feet cubed. How are we going to get from feet cubed to gallons? We look at this. We know we can go from feet to inches, feet cubed to inches cubed, sorry. And from inches cubed, we can go to centimeters cubed. From centimeters cubed, we can go to milliliters. From milliliters, we can go to liters. Liters, we can go to quarts. Quarts, we can go to gallons. A lot of steps, but it should work. So we first want to go to inches cubed. And so 1 foot cubed, it would be 12 cubed inches cubed, because you remember you have to, if you have a conversion factor that's inches to feet and you're going inches cubed to feet cubed, you have to cube the numbers 2. Technically also 1 cubed down there, but we really don't care about that because it's just 1. So that gets us to inches cubed. We want to now go from inches cubed to centimeters cubed. 1 inch cubed is 2.54 cubed, centimeters cubed. We then want to go from centimeters cubed, get rid of that, go to milliliters. And so 1 centimeter cubed is 1 milliliter by definition. We then, probably let's go ahead and just shift it down to the next one. And I'm just going to put a little ... to show that we're continuing this down here. Sometimes you'll have to do this. And so we're going to continue this across. So we have, but keep in mind when you drop this down, if you drop it down like this, that things on top and on bottom are still there. And so in this case right here, we've got milliliters on top. We want to cancel milliliters, and so we're going to put milliliters on bottom, and we want to go from milliliters to liters. And 1 milliliter is 10 to the negative third liters, like that. We now want to go from liters to quarts. And so 1 liter is 1.06 quarts. 1.06 quarts. And at that point we want to cancel quarts and go to gallons, which is what we question asks for, how many gallons of water, and 4 quarts in 1 gallon. And so to find our final answer here of how many gallons this trough holds, we'd simply say 16.755 feet cubed. So times 12 cubed going across the top times 2.54 cubed times 1 times 10 to the negative third times 1.06 times 1, and that's which on the top, divided by 1 cubed, divided by 1, divided by 1, divided by 1, divided by 1, divided by 4, our final answer. So we get for this 125.728 gallons is our unrounded answer. In this case right here, since it's spelled out 4 feet, that's exactly 4 feet. And so this would be fine for our final answer. So 125.728 gallons would be the total volume of this hemispherical trough. Just an example worked out there of how we might go apart working out a conversion problem using factor dimensional analysis.